Hello again. This is the second part of what we're going to cover today, and it's going to link over to Friday as well, okay? Because this is quite a big section. So the last section should have taken you probably no more than half an hour, and then I want you to spend no more than half an hour on this section. So once you've completed an hour of chemistry with me, that's you done for today. Leave the rest for tomorrow. We're going to look at the preparation of amines now. Okay, so we are now on the bottom of page 8, so preparation of amines. There's a couple of methods when we're preparing amines in the lab. And the first method involves reduction. So it's method 1 that we're looking at. It talks here about the preparation of aliphatic amines. That just means like straight chain amines. Okay, so that's all that means. Now, the first thing then we have to realize that this is prepared by the reduction of nitriles using lethal dissolved in dry ether. Now, you should have come across lethal before, probably with Mrs. Dempsey's topics. So you should be familiar with it, that it's just a reducing agent, and we just write it. We don't write out the full name of it. We don't even write lethal. We write an H with square brackets around it because that's the symbol for a reducing agent. So the conditions for this reaction then, this is the important thing, you've got to write this down, is that you're going to reflux. So you're going to heat with reflux with lethal and dry ether. So you could be asked about the conditions, and that's what you will write. So pause this now and write that down. Below that, you'll see we've got the example of the reduction of ethane nitrile. And what has happened here is I have just put in a general equation rather than going for ethane nitrile. So you can either just write beside this general equation, or you can manipulate this and change it into ethane nitrile. But you can see I've got the nitrile there on the left with its R group. And then I'm reacting it with 4. Lethals are 4 of the reducing agent. Above the arrow and below the arrow, I have got the conditions. And then on the right-hand side, we have got our amine, which has been produced, our primary amine. So what I want you to do is I want you to pause and draw that in just at the bottom of page 8. Now, we can then show that if you want to have the specific one for ethane nitrile, this is what you will write in. CH3CN plus 4 reducing agent, then we'll produce CH3, CH2, NH2. So there's your specific one. So get those both written in. Pause this now and write them both in. At the top of page 9, it says this. If a cyano group, that's also known as a nitrile group, remember? If a cyano group is needed to form an amine, it can be introduced by refluxing a halogenoalkane with a solution of sodium cyanide or potassium cyanide dissolved in ethanol. So what you can do then, if you don't actually have the nitrile that you need, what you can do is take a halogenoalkane, as you can see at the bottom here, react it with a cyano group, and then it produces the nitrile, and you can go on and use that then to create your amine. So what I want you to do there at the top of page 9, you'll see there's a space. I want you to pause this now and draw that in. Just below where you've drawn that, you'll see method 2 then. So that's everything you needed to know about method 1. You needed to know the conditions, you needed to know like the general equation, and you needed to know how to prepare the nitrile. For method 2 then, it's nucleophilic substitution that we're using. So we're actually starting with the halogenoalkane, and what we're doing is we're warming it gently with an excess of concentrated ammonia. So there's a bit more we need to know about this. The first thing is it needs to be ammonia, which is in ethanol, so sometimes called ethanolic ammonia. And what we then have to look at is this first mechanism. And what you'll see here is that we're starting with bromoethane. And what you can see is you can see ammonia to the side. Now what happens is it's the lone pair of ammonia is attracted to this positive carbon. Remember, there's a polarity here in this carbon-bromine bond where bromine is more electronegative, so the electrons lie closer to it, leaving this carbon to be slightly positive and therefore vulnerable to attack from this lone pair. So the lone pair attacks. We then have this transition state where we have both the ammonia and the bromine attached for a second. If you look at it, what will happen as a result of that, the nitrogen will become slightly positive, which will lead the electrons in this bond between the hydrogen to lie closer to that, which will then cause the electrons here to be pushed out because of the lone pair that's been pushing its way in here. Okay, so the lone pair has pushed its way in here, causing repulsion for the electrons to move that direction, and then causing electrons here to move in and fill the space. And that then leaves us with our primary amine, which is either ethylamine or ethane 1-amine. Okay, those are your two options there. Now, you do have a question there that says, why is the reaction carried out in a sealed tube? Well, the reason is this: you're working with concentrated ammonia. Okay, concentrated ammonia would choke you to the point where you would struggle to catch a breath. So it's seen to be quite toxic and quite dangerous. So our answer here is to prevent the ammonia from escaping. Now you can go on and explain that it's a toxic gas and it's dangerous for health and it's a health hazard, but the main idea here is to prevent the ammonia from escaping. So I want you to write that down, and that's the only thing from this page that you need to write down, that little answer there, okay? The next thing on your page says the reaction is, and in that wee space you're going to write down nucleophilic substitution. So that's the reaction and the mechanism that we're using. The first example we're looking at is the reaction of 1-chloropropane with ammonia. And I have written this down already, or I've drawn it down, and you can see we've got 1-chloropropane here on the left. We're drawing ammonia, we're keeping in the bonds and the lone pair, and then we're showing the final product. Okay, so that's a propylamine or propane 1-amine, and then what we produce is HCl at the end. So pause this video and draw that into that space. You also need to write in then just below the next bit of writing. So the next bit of writing says the acid formed by the reaction then reacts with a second molecule of ammonia to form the corresponding ammonium salt. So just below that, you're going to write in what's in this green box. So what you have then, you've produced your amine and this HCl, this hydrochloric acid in this case. What happens then is the acid then reacts with any leftover ammonia and it forms the ammonium salt. So that's what you want to write in. Now for method 2 to work really effectively, you really must have the concentrated ammonia in excess. If you don't have it in excess, what will happen is there will be further substitutions. So you won't actually end up with the primary amine as your product. That will go on and act as the nucleophile, and you'll eventually end up with something different. And we're going to look at that. Now, you're not going to write any of this into your books. You're just going to look at the screen here and see the process, and then we're going to relate that to the example in our books. So this is the first substitution. So we start with the halogenoalkane, and we start with some concentrated ammonia, not a lot of excess. We end with the primary amine, and then this NH3 plus Br minus. Okay, now it's still nucleophilic substitution. I want you to look at these two molecules that we have here. We've got bromoethane, and you can see the polarity there, okay, because of electronegativities, and you can see where this carbocation ion is becoming vulnerable to the attack of the lone pair. So what happens then is the lone pair attacks the carbon, and remember we've looked at this before. It pushes the bromine out. So we can see where there's repulsion of electrons and movement of electrons from our curly arrows. What then we have produced at the end is we totally have that bromine's completely replaced, and for a moment it's replaced with the NH3 as a whole. But we know the amine doesn't have NH3, it has NH2, so something else has happened here. Now, we still have our bromide ion, so it's been pushed out, so we're not worried about it for now. We're going to leave it to the side. We're going to focus on this C2H5N3. This isn't exactly correct for us. What will happen here is the nitrogen, because it's got 4 bonds attached, will be positive. And so the electrons from one of these hydrogens will move closer to it. Okay, it'll be attracted to that positivity. The second NH3 molecule then will suddenly start to get into action, and let's look at what happens here. What will happen then is the lone pair from that second ammonia will now attack the hydrogen, which is now vulnerable as it is slightly positive due to the electrons in the bond moving closer to nitrogen. So the final thing we're looking at here then is we're looking at our final primary amide, ethylamine, and this NH4Br, ammonium bromide. That was the first substitution. It doesn't end there. You've made your primary amine, you've ran out of ammonia, but you've still got halogenoalkane. So what happens is the second substitution here. So you've got your halogenoalkane, you've got loads of it, and now you've got the amine that you made before. And look at what it does, is it removes, the big picture here is it removes one of the hydrogens and it replaces it with another R group. So we end up with 2 R groups now and 1 hydrogen on that nitrogen, okay? So hopefully you're going to see a pattern where we're just going to be adding more and more R groups here, which is not ideal when you wanted to make a primary amine in the first place. And this time we end up with HBr because we don't have any of that left over NH3. So let's look at the mechanism here. These are our 2 molecules we're starting off with. Again, we've got the polarity in the halogenoalkane, and this time you've got your ethylamine, and remembering that that nitrogen has got a lone pair, and so it can behave in the same way as ammonia. The lone pair here will attack that slightly positive carbon and push the bromine out. Therefore, we're going to see a bond here between the amide group, sometimes known as the amino group, and the second R group. Here you can see it. It's been formed together. Look, we've got the original ethane group there, and now we've got a new ethane group. Again, there's a problem for nitrogen here in that it's got 4 bonds. Remember, it only likes to have 3 comfortably. Otherwise, the neutrality is disrupted in this molecule. So we have a slightly positive nitrogen right now. That's going to cause the same problem as before. Remember, on our bromine at the side, not forgetting about it. But we're going to find that the electrons from one of the bonds with the hydrogen is going to move in closer to that positive charge. It's going to be attracted to it. We are then going to end up with our secondary amine. Okay, so we've got 2 R groups and 1 hydrogen, and then HBr. What has happened up here that we haven't seen is that the electrons in this bond moved closer to nitrogen, making the hydrogen slightly positive, and that's when the lone pair from bromide moved in and essentially stole it. So what we've produced now is we've produced diethylamine. Okay, you've got 2 ethyl groups, so it's diethylamine and hydrogen bromide. Third substitution. So this just kind of keeps going on and on and on and on until we run out of bonds that we're able to make. What we start with is our halogenoalkane again. Same way as always, we've got the polarity difference here, and we still have our lone pair on the amine, so it moves in on that slightly positive carbon. So the lone pair is attracted to the slightly positive carbon, it disrupts the bond with the bromine, it kicks the bromine out, and it creates a bond between the carbon and the nitrogen. Again, we have the same problem of nitrogen having 4 bonds when it only wants to have 3 and being slightly positive. Hopefully you can see we've now got 3 R groups here and the 1 hydrogen. So the electrons from that bond between nitrogen and hydrogen are attracted to the nitrogen, and it leaves the hydrogen slightly positive and vulnerable to attack from this lone pair of the bromide. That then causes us to have our tertiary amine produced and HPR produced as well. So we end up with a triethylamine and hydrogen bromide. It doesn't end there. There is another substitution. Because of this lone pair, we are vulnerable to more substitutions. In the fourth substitution, this is hopefully getting repetitive for you now. In the fourth substitution, we start off with our halogenoalkane. I hope you realize that it was an excess the whole time. And we have our tertiary amine. Same process as before. Carbon is slightly positive and vulnerable to attack from the lone pair. The lone pair has attacked. Bromine gets pushed out. Now we have our, what you might call a quaternary amine right now, or a tetraamine right now if you wanted to. We're going to end up with a slightly different name at the end, but we're not worried about that. Here you can see nitrogen has caused to have a positive charge, but we have no small donating hydrogen here anywhere to donate the electrons, so we're a wee bit stuffed. What we do have is we've got the bromide ion. So what we just end up with is a quaternary ammonium ion and a bromide ion. This quaternary ammonium ion, the whole thing ends up to be positive. The bromide is negative, and when we have a positive and a negative, what happens? There is attraction. So here we have created an ammonium salt. So what we describe this as is a tetraethyl ammonium bromide. So tetra for our 4 ethyls, ammonium because it's behaving like ammonium would, and then it's bromide. So if you look at this last wee bit, it says the presence of excess ammonia reduces the chance of the amine taking part in further substitution reactions. So if you want to create a primary amine, use lots and lots and lots of ammonia. Otherwise, you start this process of substitutions, which just doesn't know when to end. Now, in your book, you are asked about substitutions in 1-chloropropane. And this is when we don't have enough ammonia. I don't want you to write down the mechanisms. I'm happy for you not to have them, just the main equations. But what you have starting at the bottom of page 9 and going on to page 10 is you have the 4 substitutions. They follow the same principle as before. Okay, so what is happening each time is we're adding on an amide group. We're removing the halogen and we're adding on an amide group, and we're ending with an acid, and that same process. So I have written down here your first substitution. What I want you to do is to draw it out and then also to write out the molecular formula. I've done that as well. So for each substitution, and you're going to do this now, you are going to draw the structural formula equation, showing me what happens each time, the same format as before, and the molecular equation. So what I want you to do is to pause this video. I have done the first substitution for you. I want you to do the second, the third, and the fourth. And each time what you're doing, if we look at this end product, really what you're doing is you're just knocking off one of these hydrogens and replacing it with this R group. Okay? Now, you don't have to draw them out like this every time because you're probably not going to have enough space. You can shorten it to just write C3H7. Eventually, what you're going to end up with in the fourth substitution is the ammonium salt. So the nitrogen is going to have 4 bonds coming from it. It's going to have square brackets, a positive charge, and then you're going to have the chloride ion beside it. So pause this now and get going on that. Okay, here is the second substitution. So you can see we start with the halogenoalkane again. Okay, so we start with chloropropane, and we are adding it now to our primary amine. What it does is it boots out this hydrogen essentially, and it adds in the R group. So we end up with having 2 propane groups there. So this would be dipropylamine and hydrochloric acid. So make sure you've got that written down, and make sure you have got your molecular equation written down. So pause this now, check your answers the same as mine, and then hit play again. Here's your third substitution. We start with our halogenoalkane. We have our secondary amine. We react them together. We end up with a tertiary amine and hydrochloric acid. And this is your molecular equation. Once again, pause and check that yours is identical to mine. Do any corrections that you need to do. Really important that you have this right in your notes. Remember, add any wee points in that you might need to do. Then finally, this is your fourth substitution. So you have your halogenoalkane at the start, 1-chloropropane. You've got your tertiary amine, tripropylamine. And what you produce is you produce this quaternary ammonium salt and your chloride ion, forming this salt together, okay? And then your molecular equation. So just as before, pause this and copy it in. We have a question at the bottom, just below the fourth substitution there on page 10, and it says, what reaction conditions should be used to ensure that further substitution is minimized? And this is what you want to do. If you want to create a primary amine, you want to prevent these substitutions from happening, or you have just wasted all of your time, and it will have been hours that you have wasted and lots of money. So you're going to probably get a bit of a telling off if you do that in the lab. So after everything we've chatted about, what is your answer here? Hopefully quite quickly you've realized use an excess of ammonia. It's concentrated ammonia you're using, it's ethanolic ammonia, you're refluxing it, but the key here is use lots of it. Make sure you have it in excess. You cannot have too much ammonia to create the primary amine. The problem is if you don't use enough, then you get into this whole whirlwind of the substitutions and you'll be there all day. Now, the last bit of preparation we're looking at is the preparation of aromatic amines, and that's amines that have like the benzene ring attached. Now, the way we do this is it's a reduction of nitrobenzene using a mixture of tin and concentrated hydrochloric acid. And you will be glad to know that you will not be asked to ever do this in a practical in school, and probably not in university, because remember, benzene's not the best chemical to really be working with too many of those long-term health hazards. So, reduction of nitrobenzene using a mixture of tin and concentrated hydrochloric acid. Make sure you highlight that in your notes, because that's important. Your conditions here, you're going to heat under reflux, and then you're going to follow it up by adding concentrated sodium hydroxide, and that's important. So you do your first reduction, and this is the bit that you do when you heat under reflux. Once you've done that, then you add concentrated sodium hydroxide, and I'm going to show you why that's important in a wee second. But before I do that, at the bottom of page 10, what we're going to do is we're going to draw in this equation. So what we can see is we've got nitrobenzene, and we've added our reducing agent. Okay, remember that's what H stands for. Part of our conditions are tin and hydrochloric acid, the concentrated version, not the dilute. So you put them in above your arrow, and we end up with phenylamine, because we've got the phenyl group, and we've got an amine group there, and we've got water left over. Pause this now and draw that in at the bottom of page 10. Unfortunately, it's not really a rosy process to get to here. There's a bit of a stepping stone we have to get between. So we're going to look at that, and that's at the top of page 11. It says this at the top of page 11. The excess HCl must be neutralized by concentrated sodium hydroxide as the phenylamine is converted into the corresponding ammonium salt, phenyl ammonium chloride. The dilute alkali liberates the amine from its salt. What that means is you start with nitrobenzene. You're reacting it with tin and concentrated hydrochloric acid. That concentrated hydrochloric acid decides to join in on the party, and it forms this intermediate where you've got NH3Cl bonded to your phenyl group. And that's not ideal. We're not trying to make that. So this is called phenyl ammonium chloride. So what you have to do is you then have to react that with sodium hydroxide, and the reason you're going to do that is to liberate the amine. That's the word we use. I like that, to liberate the amine. What we're going to do is we're going to get rid of the HCl from this and leave us with the NH2. So what's going to happen is the Cl is going to go away off with the sodium and form NaCl, and this H is going to bond to the OH here and form H2O. Okay, so that's the important thing. So it's important to know that there's a little step in between. So you need to know the conditions, these two conditions. You need to know that you've got to heat it under reflux. And then you need to know that you've got to add sodium hydroxide at the end to form your phenylamine at the very end. That is all the theory covered. So your notes should be up to date up until page 11. And now this is what I want you to do. I want you to complete the questions on page 11, and there's actually only one page of questions to do there, and then I want you to submit that to Google Classroom. Now, you've probably had to stop this video halfway through, I imagine, or part of the way through anyway during Thursday's lesson, because I think when I'm kind of adding the times up, there's probably far too much work to get done just in one lesson. So this should be spread over Thursday and Friday. And this might be a wee bit of a short lesson for Friday, but I think that's okay, because you've got your past paper to be doing as well. So by the end of this week, you should have finished up to page 11, and you've covered quite a bit of content there. We've covered your structures of your amines. We've looked at the functional group, the shape of them, how we name them, how we draw them, our different formulas in terms of structural and molecular. We've looked at our properties, we've looked at shape, boiling points, solubility, and now we've looked at preparation. So that's quite a lot. I want you to be really confident in that. For when you have lessons with me again, we're going to be moving on to the reactions of amines. So the next week I have you will have this topic finished off. Now, if you do find today that you have spare time in this lesson, you should be spending an hour on chemistry both Thursday and Friday. What you can do is start to get stuck into the questions at the very back of this topic and do what you can of them, and then that will lighten the load when you come to do that. But let me know how you get on in terms of times. Let me know if this took you the full 2 days or if it only took 1 day in terms of timings, because it's hard to know when I'm setting it, you know, how long it's going to take you, and I don't want to give you too much that you feel overwhelmed. So up to page 11 should be done, and you're submitting page 11 to Google Classroom for me today. In the background, you are doing January 2012 past paper for me, and you're submitting that just before I have you again, so you've got kind of like another week to get that done. But if there's any issues, folks, give me a wee shout. I am here if you need me. Okay? Take care.